I thank the organizers for inviting me to come here and talk about things which may be not very interesting to most of you. And this is a very ambitious title. But in principle, I'm going to talk about some aspects of ruthenium dioxide which I found interesting. And first of all, let me thank the guys who did all the work. And there is a bunch of very nice people that you see. And you will see the calculations by Todoris, by Xiadon, and by Kartik. Now, by now, it is clear what altermagnets are, or not clear, but we pretend that it is. It's this fascinating pocket of magnetic materials, as we have learned at this workshop. And I will not really talk a lot about it, and we know that altermagnets differ from ferromagnets and from antiferromagnets in that they have these fascinating symmetries which allow for K-dependent spin splitting in our electronic structure. And one of the most fundamental or kind of foundation for the field is this ruthenium dioxide material, which has been predicted to exhibit this kind of splitting, which you see in this band structure, relatively large. And together with this splitting comes also the anomalous Hall effect, as we call it the crystal Hall effect, because it is odd in crystal chirality, as suggested by Libor, Tomasz, Hyro some years ago. And the motivation for the talk is to understand how this happens microscopically, and maybe at the end also pose a challenge to experimental colleagues who study transport in altermagnets. Now, to understand what we are dealing with, let me start with a simple example. And this is the case of strontium ruthenate that we have studied some time ago. Now, what I show you is a calculation of a monolayer of SRO in a structure which does not support the anomalous Hall effect. It has an inversion symmetry, and it has mirror symmetry, so the anomalous Hall effect here is actually forbidden when you include time reversal into consideration. So what you do is normally you minimize the energetics of the system, and you realize that actually it's an antiferromagnet. It's an antiferromagnetic monolayer, and it is known experience.
It's an antiferromagnet in thin film.
Yes. Sorry, I should have mentioned that it's known to be antiferromagnetic up to 4 monolayer limit. Now, what happens is this known to many of you octahedral distortion. So this oxygen octahedra, they rotate. And if you look at it, you realize that this is basically an altermagnetic phase. Yeah? So you see the C4 symmetry quite clearly. However, to see the fingerprints of it in the electronic structure is not so easy. So if you take a look at the band structure on the left and band structure on the right, there is not much difference that you see. Of course, you see a lot of difference because the effect of this rotation is drastic on the chemistry. But in terms of spin splitting between up and down, this you don't see. And you really have to zoom in at the electronic structure to see that there is a very minimal, like 10 millieV exchange, or I call it wrongly exchange. It's not exchange splitting, spin splitting between the states. This poses a certain challenge already at this step, or I can add here to Igor's talk, whether we can control the degree of this altermagnetic splitting by sort of tuning this octahedral distortion in oxide, but this is kind of a side question. Now, these bands are slightly split, and in the language of Libor, Tomasz, Hyro, these are weakly altermagnetic bands. However, what fascinates me quite strongly in this is when I look at the Berry curvature, which comes together with this spin splitting. And what I see is actually quite fascinating. This is not something that you expect from a normal anomalous Hall effect as it happens in ferromagnets, because here we have really like charged sheets of split bands which give sources of the Berry curvature in this material. And this is, I have to tell you, this is not very common in many materials. Now, this small splitting actually gives rise to a very large anomalous Hall effect, a crystal Hall effect, that is comparable to those in ferromagnets. And it also leads to what we call the crystal magneto-optics. But the bottom line of the story is that all sorts of transitions kind of matter for the response of altermagnetic materials. Let's take a look at the ruthenium dioxide. And this is something that we have also seen in the talk of Hayo, for example. The electronic structure of ruthenium dioxide is quite simple and quite clean. Spin orbit has some effect, so it causes some band splittings and some openings of the gaps. However, we are interested in the states around the Fermi energy, and this is the Fermi surface of this material that you see. It is quite well known by now. It's a hallmark of altermagnetic materials, if you wish. It is beautiful. It exhibits the spin splitting in the reciprocal space. And what I do is just I mark the bands. So I mark the strongly altermagnetic bands as bands A and B, and I mark these sheets of bands which are SRO-like. I mark them as band C. So first ones are strong altermagnets. The other one is weak altermagnetic bands. Now, when we talk about including spin-orbit interaction and response, like anomalous Hall effect, I want to distinguish also three types of crossings or transitions which can happen. And the first one is type 1. It happens when the bands of AB type and C cross. The second one is the type 2, and this is quite an interesting case where the bands of AB type cross at the brilliant zone boundaries, as you can see. And the type C is these transitions between these weakly altermagnetic bands. Now, let's take a look and see how we can see these things in Berry curvature distribution. Here you see the Berry curvature distribution for 1, 1, 0 direction of the nail vector. And
elaborate on what's weakly altermagnetic?
Weakly altermagnetic is, so in the language of Libor, these are the states which are basically split slightly by anisotropic exchange interaction, if I understand this correctly. So if you read the review of Libor, and maybe Libor can comment on this, there are two cases of states. The states which are when you have non-magnetic case, they are degenerate, and the case where the states are already non-degenerate in the non-magnetic state. So you can have the crystal field like splitting between the bands of opposite spin, but when you have the states which are not spin split, they will weakly feel this anisotropic environment for hopping in the up and down sublattice, and this causes these slight changes in your band structure, right? Libor, maybe you want to comment on this?
I do want, but I think it's pretty good.
Okay, yeah, so we can discuss about this. This is maybe just a brief statement. So let's take a look at the distribution of the Berry curvature. And here, the type 1 marked with arrows in the plot is we can identify as kind of wild points which contribute strongly to the anomalous Hall effect. You can see the distribution of these wild points in energy here, and this is due to these pseudonodal lines without spin-orbit interaction between the bands of the same spin, which gives rise to these contributions to the anomalous Hall effect, at least in our electronic structure calculation, because there is a certain ambiguity as well in how you actually compute ruthenium dioxide. The second type of transitions is due to these crossings between strongly altermagnetic bands, and the funny point here is that they cross at the high symmetry planes, and they have to because of the crystal symmetry of your lattice. So that's why these transitions contribute in these points in your brilliant zone that is basically on high symmetry planes. The third type is what we call ladder transitions between the sheets of weakly split altermagnetic bands. And we call them ladder just historically. I will say a couple of words about it in 1 minute. If you cut your band structure along a high symmetry line, they will look like this. They will look like sort of bands with similar dispersion which are crossing the Fermi energy. And you have to account this ladder transition to calculate the Berry curvature and the anomalous Hall effect. You see it very nicely in this band structure where we have small splitting without spin-orbit interaction. Spin-orbit changes this a bit, but we have this kind of peaks in the Berry curvature, which will also move as you move the Fermi energy without changing too much in magnitude. This type 1 and type 2, I think these are kind of characteristic altermagnetic transitions, which are not happening so much in ferromagnets or PT symmetric antiferromagnets, because in one case we have a symmetry enforced position of these features in your electronic structure, and in the other case we need this kind of crystal symmetry, small breaking between the states, which also does not happen that often. As I say, this type 2 and 3, they are robust features, so they don't change a lot when you change the Fermi energy. Now, let me say a couple of words about these ladder transitions, and that's the term that was suggested some 12 years ago. And I've been talking about this in 2011 at a workshop in Halle. This is an exact replica of the slide, and I think it's only Stefan who has been present in that workshop at that point. We came to these transitions because we were studying the effect of spin-conserving versus spin-flip parts of spin-orbit interaction on the anomalous Hall effect. So at that point, we knew that the spin-flip spin-orbit matters a lot for spin relaxation and for the spin-Hall effect. However, the question was very natural, so what's the influence on the anomalous Hall effect? And we took the case of L10 iron platinum, which is a very popular ferromagnetic uniaxial material, where we have shown that the spin-flip transitions can give you the entire anisotropy of the anomalous Hall effect in this material. If you look at the electronic structure of iron platinum, you see that these ladder transitions, they're like everywhere in the electronic structure. And this you can also nicely see when you analyze what we call the spectral anomalous Hall conductivity. That's the density of contributions to the anomalous Hall conductivity between occupied energy 1 and unoccupied energy 2. And these ladder transitions you can see as lines in this kind of spectral distribution. It's quite nice because that's really what should be happening if you have these kind of things. They are strongly anisotropic because when you change the magnetization direction here, you see that the monopole physics comes into play. Libor, question? No. Okay, you look like you are questionable. Now, these ladder transitions actually are more universal than you think. And take a look, for example, at this paper, which is probably known to some of the people present in the audience, I would say. Here, what was done is a two-dimensional PT symmetric antiferromagnet was coupled to a Rashba surface on one side, and as a result of this, you have kind of sheeting of your bands of spin-up and spin-down character again. And the very same people who are sitting in the first row were arguing that this kind of effect on anti-damping torque should give you a torque which is order of magnitude larger, not him, than in the ferromagnetic material. Now here we substituted the crystal symmetry in this sheeting with spin-orbit interaction. However, you can also realize this substitution by canting. And for example, if you take manganese to gold, which we all studied very intensively in the past, and you take a look at the electronic structure in the collinear state, it's a doubly degenerate electronic structure. But when you do a little bit of canting, you also have kind of band splitting of this kind. And if you look at the Berry curvature, contribution to the anomalous Hall effect, it will also have this kind of plus minus sheets of charged bands contributing to it. And that is the reason why the chiral Hall effect, that's how we called the Hall effect proportional to chirality in antiferromagnetic materials, can be truly gigantic. So at the end of the line, these ladder transitions, which may be kind of not really interesting to most of you, are in principle universal, and they appear in altermagnets quite naturally. Now, this type 2, type 3, which is also nice, are the spin-flip transitions, and again, some aspects which are pretty special. That is because the spin-conserving transitions, that is type 1, appear in the first-order perturbation theory to the anomalous Hall effect. And the spin-flip transitions of type 2, type 3, they appear in the second order only. They don't come in the first order. That is interesting because you can actually try to engineer the magnitude of these things, of these features, but also it tells you that they react kind of differently to the crystal environment, which is accumulated and averaged by the strands of spin-orbit interaction. This you can check by explicit calculations by daring to put your spin-orbit strands in ab initio to minus the value of what you have. That's a crazy experiment, but actually you can numerically do it. And also you can understand, based on this difference, the anisotropy in ferromagnets that we enjoy so much. In non-magnetic materials, normally the states come in complete subspaces of spin-up and spin-down. And if you have an opening somewhere of your Fermi surface, you have a band gap opening, it will be realized either by spin-conserving or spin-flip spin-orbit, whether you choose your spin quantization axis along Z or along X, it does not matter really. But in ferromagnets, and in large extent in altermagnets, it is the fact that these spin flip and spin conserving transitions occurring at different points in energy and in K, which gives you this breathing quality to your Fermi surface and also to the transport properties that you can have. Now, as a result of this, we have a strong anisotropy of crystal Hall effect in ruthenium dioxide. And I have to say that what is really remarkable here is the point here, that is the fact that you can completely kill off the anomalous Hall effect for some direction. That is not something that you achieve from in a bulk material like iron, where you can rotate your magnetization all you want, but it still will be around 700. The anisotropy of Berry curvature is visible in these plots, but let's also take a look for the last part of the talk at the thermal effects. And those I access by looking at these transport coefficients, which are related to thermal conductivities from general theory. Now, the anomalous Hall conductivity is the 0th transport coefficient. The anomalous Nernst is the 1st, and the thermal Hall conductivity is the 2nd. Now, anomalous Nernst, you know, it's a transport of charge, which is transverse to the temperature gradient, and thermal Hall is a transport of heat perpendicular to the temperature gradient. And of course, the anisotropy of your crystal Hall effect, this distribution of the Berry curvature, translates, for example, in strong anisotropy of the anomalous Nernst effect in your ruthenium dioxide. And here, explicitly, you see this behavior which exhibits strong anisotropy when I take my n from 001 into 110 direction. If you take a look at magnitude of these effects, you realize that this is pretty much comparable to the magnitude of the transport effects that we also observe in manganese 3X compounds, such as manganese germanium or manganese 13, which is also meaning that we can also replace all these things that we're so happy about with these non-collinear magnets just by simple altermagnets, simple or not simple, while retaining the strong anisotropy of this phenomena also as an addendum. Now, let me talk about another exotic aspect which we found interesting, and that is the Wiedemann-Franz law as we have analyzed it in ruthenium dioxide. So, what is Wiedemann-Franz law? It basically tells you that there is a relation between the electrical conductivity and the thermal conductivity. And that is quite logical. So electrons move, and they also transport heat with this motion. Now, there is this kind of constant, which is known as the Sommerfeld constant, but even away from 0 temperature limit in which this Sommerfeld expansion is done, you can plot this Lorentz ratio, that is the ratio of kappa versus sigma divided by T, and you can look at it, how it behaves. And actually, in case of ferromagnets, this has been studied quite extensively. And what is normally observed is that there are strong deviations from this ratio away from the 0 temperature. And that is normally attributed to the role of inelastic scattering versus intrinsic scattering in these materials. That is also easy to understand. So when you increase the temperature, it's easier for electrons to lose energy by scattering inelastically into phonons. And below the Debye temperature, well below the Debye temperature, that's the main mechanism for actually losing heat, of your electronic flow. This becomes more difficult once you're approaching the Debye temperature, and that's why normally this Lorentz ratio is restored when you go to TD. However, there is also this case of manganese 3 germanium and manganese 3 tin, where it is very well known that they are intrinsically dominated and there is really negligible inelastic scattering. And that is something that, don't ask me why. I can just give you the references where all piles of thermal measurements were done and where these conclusions were reached somehow. However, here you still see this deviation from the Wiedemann-Franz law as you increase the temperature. This is particularly visible for manganese 3 germanium as you start doping it, for example. So, what does it come from? And there is actually a simple explanation, which is very appealing to me because it's purely theoretical. And this comes from the fact that you have to look carefully at this pondering function, this Fn function, which enters into the integral over temperature of your 0 temperature anomalous Hall conductivity. So this is the F0, F1, F2, and the Wiedemann-Franz law tries to put together F0 and F2, or their ratio. And what you realize when you do some analytical analysis is that in the 0 temperature, the Wiedemann-Franz law is satisfied entirely. But once you start increasing temperature, these two functions here and here, they actually start probing different regions in energy. And that means they probe different features in your anomalous Hall conductivity. So the deviation from this law can be caused just by the specific electronic structure of your material. And there is also a special law coming with that. That means that if your conductivity is purely antisymmetric in the vicinity of chemical potential, the Wiedemann-Franz law will be satisfied. So you will get like a flat line. And that is the type 1 of our ruthenium dioxide. That's what kind of would be satisfied in this context. While the type 2, on the other hand, as I said, we move Fermi energy, nothing happens. It's a robust feature. The distribution is symmetric. And here, the Wiedemann-Franz law should be violated. Now, by explicit calculations for manganese-3 tin and manganese-3 germanium, you can see the validity of this picture. So here, you have this while point. And if you put your chemical potential there, this a flat. It's a flat line. Now, let's take a look at our calculations for ruthenium dioxide. What happens here looks relatively complicated. And again, one can discuss which calculation is more correct. So there is Libor's calculation, there is our calculation. They are all slightly different. However, they have all some sort of features. So I'll talk about my features and my predictions. And they are also in part Libor's because he is a part of this project. So you can put your chemical potential where you want, and you can study this Lorentz ratio behavior. What you observe is that it's very sensitive to band filling. That's good news. That's something you can check experimentally, and here I'm talking to experimentalists mainly. There are two regions in energy where this Lorentz ratio is good, so the Wiedemann-Franz law is flat, and this can be easily identified with this kind of fixed points in your conductivity temperature dependence. And this happens exactly because at these points, your conductivity is purely antisymmetric. Yeah? So here, you get these flat lines, everything is good. You look in experiment, and you know where you are in your electronic structure. You know that you are somewhere at the while point of your altermagnetic material. On the other hand, there are some clinical cases where you change the temperature a little bit, and it drops, and it really doesn't behave well. And then you know also where you are. So you know that you're in the region dominated by type 2 or type 3 transitions. And can we use this kind of thermal kind of measurements to justify what type of transitions we have? And let me pose an experimental challenge of a kind. Can we generally use anisotropy of electrical and thermal measurements? Because thermal measurements, they give us the feeling for the spread of our transport in energy, which is also very important, to identify the position character of different types of features and whether we could map out more precisely the information about the behavior of electronic structure around the chemical potential. This is something which Hayo cannot do because he is looking only below the chemical potential, but he has no access to this upper part, really. Yeah? So that's my challenge, but at the end I would like to say a couple of words more, if you give me 1 minute. Ruthenium dioxide is a very bad material because it has inversion symmetry. So it has inversion symmetry with horribly ruthenium atom as an inversion symmetry center. So in my world, this is bad news because, you know, we work a lot on spin orbit torque, and in spin orbit torque, that's a killer. So you have no spin orbit torque. Yeah? You can have all sorts of orbital Hall effect, spin Hall, and anomalous Hall effect physics, but there is no orbital or spin accumulation, and correspondingly, you cannot switch this material in bulk by spin orbit torques. So what do? We go to the second order. We go to the photo-induced effects, and that is also something that Alexei is going to talk tomorrow. But it appears that in these kind of structures, which are also very popular, this is the majority of our materials, it is the nonlinear effects which start becoming important, where you can create the spin polarization only by going into nonlinear regime, and that's where you can actually switch. And I think this is very interesting, and I all motivate you to go to the poster of Todoris and Diamantopoulos. This is his picture so that you don't miss him, even if he hides somewhere behind the poster. And what we find is that in ruthenium dioxide and cobalt difluoride, he also calculates, we find a very anisotropic and canted response of our spin and orbital accumulation in response to laser light, and also very drastic response in terms of magnitude, depending on the frequency. So this response that we find is larger than any we have found in any antiferromagnet that we looked at. Not ferromagnet. In ferromagnets, it can be even larger. But in PT symmetric antiferromagnets, you will not get that kind of optical response, which is good news, I think, for optical physics with altermagnets. But please come to the poster, and we can have more discussions about this. I think I have some kind of questions posed to the community, which one can address. I can talk about it or not. But I think it's a good time to finish the talk. And thank you for listening to these specific aspects of electronic structure of ruthenium dioxide. Thank you.
Thank you very much.